Hello, hope you're having a great day. So today we're going to take a look at the two-sum problem. The problem statement is as follows. Given an array of integers, nums and an integer target, return the indices of two numbers such that they add up to target. You may assume that each input would have exactly one solution, and you may not use the same element twice. You can return the answer in any order. Right. So we are given three different examples. So really this problem is quite simple. We have an array of numbers and we need to sum two of them together to a specific target. So in the given example, we have 2, 7, 11, and 15 and a target of 9. So if we sum up 2 to 7, we get 9. So we get the output of 0 and 1 because remember, what we must return is the indices of the two numbers, not the numbers themselves. So there are multiple ways to solve this problem. In an actual interview, you probably would be expected to give the optimal solution, even though I think the brute force is accepted for this one. So I am guessing you already know that for the brute force solution, all we have to do is write two for loops, right, and compare the nums of I with the nums of j, and if it sums to target, then we have our solution. But let's delve more into the examples before we go to the code. So let's take the first example. So we have the numbers 2, 7, 11, 15, and we have a target of 9. So then we can also note down the indices here. So 0, 1, 2, 3. So right away we can see that 2 plus 7 is 9. So that means you will have solution 0 and 1. So if you would iterate through nums of I and nums of j, we would just compare 2 and 7, and we found the solution, and we're done for this particular example. Then we have another example, 3 to 4, 3 to 4, and the target of 6. Target of 6. Okay. So that's great. So for this one, we can see that the solution would be 2 plus 4 equals 6. So we would have indices 1 and 2 as the solution. So 0, 1, 2. So yeah, you can see just comparing the numbers, using two for loops and iterating and comparing the sum with the target yields a correct solution. We just have to return the indices. So let's see how that looks in code. And we iterate through the array, starting from the first one, and then from there we go forward for the second, for the I plus 1 for the next item, and we compare all of them. If num of I plus nums of j is target, we return the indices. And actually here we also have to return an empty vector if we don't have a valid result. And you can run this, and you can even submit this, and as you can see it works. However, during an actual interview, this may not be the best solution for you because it's not optimized. So the interviewer might ask you a follow-up question: how would you do this in a better way? How would you have it optimized. So usually there's some kind of trade-off, right? There's no magical uh, bullet here. So what you would do is think how you would use some kind of space, right? Because right now we are not using any space at all. Maybe there's some way where we can take this O of n squared solution to O of n and use O of n space. That could be an optimal approach if such a solution exists. So how would we do this? Well, let's think a bit about this problem. One way is to cache some of our items, right? So if we cache uh, some individual or intermediate values, we can use something like a map or a set to then access these values and simply return our resulting target. So let me remove this. Right. So, okay, now that we are at this point, let's think what how we would do. So we would probably still need one for loop, right? So for I oh sorry plus I so we have our for loop. So one thing we can do now is we can take the complement of the number. So we can say, okay, we have a target and we have the current number. So that means we have the complement is target minus nums of I. And what this gives us is the other nums of j that we had before, right? So this is the complement. In our hash map, hash map, we're going to have I'll just call this hash map for simplicity. And here we store in the hash map for our current value, we store the index because we want to return the indices, right? So we have our complement and we have our indices in the hash map. So then what we do now is we check if the hash map contains, you can check this also with find, but I'm just going to use count, contains the complement greater than 0. So if there's at least one instance of this, which is going to be true if the complement is already there, then we have our solution, right? We already can return the hash map of num of I, of complement, and the current index I. So instead of having nums of j and nums of I, we are using a hash map to get our solution to O of n time and O of n space. So we increase the space complexity and reduce the time complexity. Right, so let's go through some examples using the hash map solution. So like we said, we are going to use a hash map. And originally the hash map is empty. And if we take the first example, we're going to have I equals 0. And then we consider number 2, and we put it in the hashmap with the uh, index 0. So that's our first entry. And we check here if, so it's our complement in this case. Our complement is going to be 9 minus 2 equals 7. So 7 is not currently in the hash map, so we don't have a solution yet. And then we go to I equals 1. I equals 1. And then we have 9 minus 7 equals 2. And surprise, surprise, now we do have 2 in our hash map. So we don't even add the second value here because we already have our solution. We know that 2 plus 7 is going to be 9. So the complement here 2, we return a solution of hash map of 2, which is 0, and the current I, which is 1. So this would be 0 and 1. 0 and 1. So that's this example. Let's take a look at the second example. So again, we start with an empty hash map. And let's consider again I equals 0. So we have 6 minus 3 equals 3. 6 minus 3 equals 3. And we put our current 3 in the hash map with index 0. Then we have I equals 1. And we have 6 minus 2 equals 4. This is our complement. And here we can see that 4 is not in the hash map, so we add this current number 2 with the index 1 to the hash map, and then we go to I equals 2, and here we have 6 minus 4 equals 2, and this time the complement 2 is in our hash map. So what does that mean? That means we have our solution. Again, our solution would be hash map of 2, so that would be index 1 and current I. So that means we have solution 1 and 2. So this is a good example of how we can decrease the time complexity using the additional space complexity in this example represented by a hash map. As we know in C++, the unordered map is the hash map and the regular map is based on red-black trees. So that would be logarithmic in time, while the hash map gives you constant time access when you search for the complement. That's all for this problem. Thank you for listening. Hope it helps, and stay tuned for more C++ problems. See you. Bye.